we will go through stratification. See, I'm going through the slides right now, and at the end of it, we'll put everything together like we did in the define phase. In the measure phase, at the end, we'll put everything together. Okay, this is what you do in measure. After this, you do this and all that. And then at the end, we will walk through the entire DMAX cycle and say, when you initiate the project, this is what you do, this is what you do. And then, we will walk through the entire DMAX cycle. So at the end, we will try to knit everything together.
Okay.
Okay, because there are a lot of tools, a lot of techniques which are there, and we have, Greenbelt doesn't cover everything as well. So, we are trying to go through each and every technique. Some of the tools might be used in some of the projects. Some of the tool might not be used in some of the projects. Okay. Coming back to the presentation, stratification. What is stratification? You are stratifying the group. Okay, you're stratifying the data into a different homogeneous group. Okay, so it can be, so given an example, defects, for example, it can be stratified by process, by nature, by shift type, by experience, by volume per CA, by, I don't know, by volume per, what does CA means? By person. So the intention is that defects can be stratified into different categories. So any data that you have, you can actually do the data stratification. When you're doing data analysis, you should not look at data as a whole. You should try to segregate data, segmentize data, stratify the data, and then try to draw a meaningful reference out of it. And then a very important thing, which is sampling techniques. Now, is that limited amount of data which is representing or representative of the population. Okay, so in statistics, population is often denoted by capital N, wherein sample is denoted by small n. Okay, why we do sampling? Any guesses, or you want to give it a try? Why do you think we do sampling?
At some point, there's just too much data, right?
Absolutely. Absolutely. It is not possible to study the entire population. One, we might not get the entire population data. Second, it will be very expensive to study the entire data. So we don't want to spend that much amount of money or effort in collecting the population data, then checking whether the data is correct or not. And it'll be very expensive exercise. So what we do is we draw a sample from population. So sample is generally drawn which is representative of the population. All the statistics that we see, it is based on this concept of sample being representation or representative of the population data. Okay. Okay, some sampling types. Now there are various others. So what we are covering is random sampling. What is random? Random is you randomly pick up the samples from the population following any technique, any assumption, right? Then you take a systematic sample. What is systematic sample? Let's say, I have 1000 data set. I want only 100 data points out of it. So I'm saying, let me pick every 10th data point. So what I've done is I've taken every nth item from the population. So it is a systematic sampling. Then we have a stratified sampling. What is stratified? I have divided the data into certain subgroups and then take a random sample from there. And then convenience sampling. Convenience is, I might not have the entire population data available. So I will pick up the sample from whatever I have available. Okay, so that is convenience sampling. So, we say sample should be representative of the population. Okay, and while we do sampling, we need to avoid, there's something now called as bias. So bias is that I know, this is the area where I would probably get the maximum defect. So I'm trying to improve a project on defect, and I'm trying to do the baseline. I would pick up samples from there so that my baseline looks very bad, right? And when doing the final project, trying to assess whether I've done the improvement, I have picked up the sample from an area where probably defect doesn't occur, or I have taken the entire population data for all the area while doing the comparison. Okay, so that is called bias sampling. What is the methodology of sampling? Pretty simple. You select a sample from the item, measure the characteristic, calculate the sample statistics. We will understand how do we calculate the sample statistics. How many sample do we need to pick? Is something that we will check, and then provide the sample statistics at the estimation of population statistics. Now we'll get into a bit of statistics here. And let's first understand it with the help of example. So what is the sampling methodology? Let's say we want to collect a sample average height of the students in a college, and we have a population, let's say 100 students. So what we have done, we have measured the height of all the 100 students in the sample, and we calculated the average height of 100 students, which is 5.5 feet. So remember, we initially started. Okay, so what I was saying, you would notice here as well, we have taken the average, right? So although initially I said that average is bad, we should not look at average and all that stuff, but unfortunately in statistics, everything is calculated based on average. And the reason why we do that, because it is assumed that data is distributed normally, right? So normal distribution is assumed. So that's the reason why a lot of statistics, a lot of tests that you would see would be based on averages only. Okay, I will move ahead to the next slide. Now there's something known as confidence interval. Now we will not dwell too much into the formula. A formula is there on the slide. You would be able to read it. Let's try to get into the concept of what is confidence interval. So have you heard about this term earlier, confidence interval?
No. Oh, continuous data, yes.
So
Okay.
no, not not continuous data, confidence interval.
No, I've never heard of that.
Okay, so in statistics, we can never say we are 100% confident. There would always be some margin of error. Statisticians always want to play safe, right? So they would always say, I'm 95% confidence, or I want to be 95% confidence. 5% is a contribution of error that we have, is a contribution of chance that I'm willing to accept. Okay, so let me just try to explain this concept. So 1 second. So in statistics, you would often see, what we say, if I want to be 95% CI. CI is confidence interval, right? So overall, it can be 100%, right? I want to be sure 95%. So what is remaining?
5%.
Is 5%. So with data, I want to be sure 95%. Or let me say surety. And this is just an example I'm telling you. There's no word as surety in statistics, right? I'm just trying to explain the concept. So 95% is surety, 5% is the contribution of chance that I am willing to accept. Okay, so in statistics, it is called alpha. So it is denoted by this symbol here, alpha.
Okay.
So alpha is 5%. So confidence interval is calculated as 1 minus alpha, which is this. 1 minus alpha is the confidence interval. Okay. Now there is something known as standard error. So how we calculate? So we'll just go through a definition. or rather the example, and then once we calculate the sample size, that is where we'll see, you know, how these things are getting used there. So standard error is basically standard deviation of the sample that we have collected divided by under root of n. So n here, if you see here, n is small n, which is for sample. So if we have 5 sample size, so it is under root of 5. Okay, this is how you would calculate for continuous data. If you have a discrete data, it is again the same. The standard error is calculated as p, which stands for proportion of defect, multiplied by 1 minus p divided by n under root of same. Okay, so not dwelling too much into it, rather getting into finding out the confidence interval. So confidence interval is basically the range. Okay, so if we look here, what we are saying is sample mean plus minus a constant confidence level. So there are two things. One is confidence level and other one is confidence interval, which will be much clearer when we look at this particular example. So what we're saying is there's a data of talk time, and the data for talk time for the call is normally distributed. And the random sample of 10 calls is selected, and their talk time within seconds are these. So what it is asking us to do is calculate 95% confidence interval of the average talk time. Okay, now how we calculate average? We know we have the data, we would be able to calculate average, which is here 47.70. We would be able to calculate standard deviation as well, 5.87. Number of data points 5 and 2 rows, we know number of data points are 10. So how we calculate confidence interval? Average, which is 47.70 plus minus 1.96. So for now, just remember at 95% confidence, the value that we need to take is 1.96. I will explain you why we have taken 1.96 when we do the Z calculation. Okay. So for now, just say that in the formula, it is always 1.96. The confidence interval that we have taken is 95%. So it is 1.96 into standard deviation divided by under root of n, which is 10. So it has given us 47 plus 47.70 plus minus 3.64. Okay, so this equation here has given us 3.64. So the confidence interval that we have is from 44.06 to 51.34. This is how you would calculate confidence interval. You would never need to calculate it manually. Okay, so you would, so I will, let me just open Minitab. Did you get any response from Minitab, folks?
No.
Oh, you haven't? Okay.
No.
So, in fact, let me just take any data for that matter, this data. The statistical software, I will, so this is this easy. See, it has given me confidence interval.
Nice. Okay.
So I didn't need to put in or memorize those formulas and then go ahead and calculate, right?
I see why you like it.
Yes, absolutely. But the concept is this, you know, 95. Where is that Excel? Concept is this: 95% CI. So my alpha is at 5. At 95%, the value is 1.96. Right, I put the values in the formula and I get, you know, my confidence interval. Easier is I put the data in Minitab and I get confidence interval. I let Minitab do the calculations. Okay, now for discrete data, random sampling 80 transaction monitor, 10 are defective, calculate 95% CI. Same thing, you have the values, sample population 10 defects or 10 defected divided by overall transaction monitor, you got 0.125. 0.125 is the proportion defective. We have calculated proportion here. P plus minus 95% CI, which is 1.96, under root of P multiplied by 1 minus P divided by the sample, the same formula that we saw here. Okay, we're just putting the values in this formula, and it has given us confidence into it. Okay, now the sample size. How do we find out which is the correct sample size to calculate from the population mean? Some example. So we're trying to calculate the correct sample size. So with 95% confidence, you would often see confidence as 95%, right? So generally, as a standard, 95 is taken unless and until you are dealing with something very critical. So we need to determine whether the mean diameter of a fiber optic cable differs by 0.5 mm. Now it is known that the SD, which is standard deviation, is 2 mm. Okay. Now first I'll show you the formula, then I'll show you the Minitab, and then I will show you, rather I'll not show you Minitab, I'll show you the calculator. Okay, the sample size is Z alpha by 2 multiplied by standard deviation divided by E and square of everything. Okay, so here we got the value of E, which is error 0.5 mm. Standard deviation we have 2 mm. Z alpha by 2 is 1.96. Okay, so just remember right now it is Z alpha by 2 is 1.96. Alpha is, remember what is alpha? Alpha is 1 minus confidence interval. Okay, sample size is 1.96 multiplied by 2 divided by 0.5, which is E. So we got a sample size of 62. Okay, so out of 100, out of whatever sample that we have, if we have these values, we know that we need 62 is a statistically significant sample size. Okay. For discrete data, again we have the formula to calculate sample size. All we need to do is we need to put in the figures in the formula. So it has given us proportion defective. It is known P proportion defective is 0.15. Okay, so again simply putting in the formula, we are getting a sample size of 197. Okay, now it is asking us to repeat it with the confidence interval of 99%. Now before we do that, we will do that later on, but then before we do that, we would need to understand how do we, so where does this 1.96 come, where have we got this figure from, right? For that we would need to understand what is Z and how do we calculate Z and what is Z table. Although it is not covered in the curriculum, but I think I would quickly tell you about it so that you are aware. So just give me a moment, let me just pull up the Z table.